Okay, welcome everyone to the Astronomical Society of Edinburgh. We have an interesting talk from Dr Rebekah Higgitt tonight about Nevil Maskelyne and the global projects of the 18th century astronomy. And we have another few things as well. So we'll have a few introductory remarks, what's coming up next, and our main talk. We'll have the sky in January from Alan Pickup. Will Joy is going to tell us about his meteor right, meteor wrong results. We had a quiz about that a couple of months ago, and I'll cover the winner of our Image of the Quarter competition. So welcome wherever you are in the world. We've got people from Dublin, Milton Keynes, Portugal, and Rhode Island, USA at the moment. Wherever you are, you're very welcome. We have four recent new members over the last few weeks. Stuart Charman, April Robertson, Paul Summerling, Fabian Yee. So I think some of them are on, so we can unmute and welcome them in the usual way, please. Hope you enjoy being members, and if we can help you in your astronomical journey, then let us know how we can do that. And the membership's up to 160 now. Fees are very reasonable. And a reminder for those members who haven't paid yet, there's 27, I believe. Alan will be emailing you. You don't want to miss out on being a member of the society. You'll get dropped into a black hole at the center of our galaxy, so don't get spaghettified. That's the last thing you want to do. If you want to stay in touch with us, there's lots of ways of doing that. We have a website. We're on Facebook and Twitter a lot, and all the videos of our meetings over the past few years, as this one will be, are on our YouTube channel as well. And there's lots of videos worth watching too. And we have people from Edinburgh and Vancouver just popped up as well. This is what we have coming soon, the next few meetings. Next Wednesday, we have our Imaging and Observing Group. That's for ASC members only. On the 21st of January, an online meeting, Building Galaxies One Star at a Time, from Dr. Elizabeth Stanway. The 4th of February, Giles Hammond from Glasgow University will be telling us about the 20-inch Grab-Parson telescope that they've been upgrading at Glasgow University. As for today, this was meant to be a hybrid meeting, but obviously we had to make it just online. We don't know what's going to happen in February yet, but I'll keep you up to date via the newsletter and through the website as well. Hopefully it won't be too long before we can get back to physical meetings again. On the 18th of February, an online meeting from Lynn Smith of the British Astronomical Association about the red sun. The 4th of March, again, maybe hybrid, maybe online. Gamma ray bursts, black holes, neutron stars, and gravitational waves from Dr. Max Rivett. And we have, on the 9th of March, we have an Imaging and Observing Group meeting for ASC members with Bruce Waddington from the USA. He was involved in developing the guiding program that we all use, PhD guiding. So that should be a really interesting meeting for us as well. And on the 18th of March, we have a talk from Whittam D. Reeve about meteor trail reflections observed at Anchorage. So lots to look forward to. We have other meetings lined up, but those are the next few. So without further ado, I'm going to hand over to Rebekah. I'll stop sharing. Rebekah, if you want to take over now and take it away. Thank you.
Okay, hopefully you can see my first slide. And I'll take it away.
Yeah.
Thank you. So yes, the talk I'm giving today is really based on work I did a little while ago now. So while I was a curator at the Royal Observatory in Greenwich, shown in this image, I wasn't there in the early 19th century, but a little while back in 2008 to 13. And also when I was part of a project that overlapped with that time, which was funded by the Arts and Humanities Research Council between Greenwich and Cambridge on the history of the border of longitude, which will come up during this talk. And that project was back in 2010 to 15. And there are a number of books, publications, exhibitions, and so on through those times relating to some of this material. Of course, it's still relevant to me now as curator at National Museum of Scotland, responsible for things like astronomical and surveying instruments and so on. So these things remain sort of dear to my heart. But I am focusing on Nevil Maskelyne, who was Astronomer Royal at Greenwich. So I will come back a bit more to his biography, but he spent 46 of his 79 years at Greenwich from when he became Astronomer Royal in 1765. The talk, though, is also going to be a bit about what astronomy was like and what astronomy was for in the 18th century. And of course, the extent to which in this period it was becoming, in many ways, a series of quite global kinds of projects. It's an era, of course, before anything like scientific research as we would understand it now was funded, as the Royal Observatory in Greenwich was by government. So if you Google, as I'm sure you know, the word astronomer, you're likely to come across images like these. And it's true that in the past, professional astronomers probably did spend more time looking actually through telescopes than they do today. But certainly the popular idea in the past and the popular idea now is of astronomers as stargazers, essentially, looking at the heavens, an appreciation of the skies. And that's, of course, really not at all what the position of the Astronomer Royal in Greenwich was all about in the 18th, 19th century and beyond. Maskelyne and others were actually not stargazers, but star and moon and planet and sun measurers. So it's really all about measuring positions and recording tables and data, creating ever more accurate maps, sense tables of the positions of the fixed stars, and theories, improving the theories of how the moon and planets moved against them. And of course, looking at data like this is clearly not something you just do for fun. So who was Maskelyne? This is a slightly later image than the previous one I showed you, which was the man sort of in earlier middle age. This is in 1785 when he was 53 by Van der Poel, and it says quite a lot, I think, about how he wanted to be remembered. He's given an impression of himself here to the people looking at him in the future as a Doctor of Divinity. He's wearing clerical dress. He was ordained, as a number of other astronomers royal were before him, and indeed other astronomers at the universities and so on. He is also, of course, though, clearly here the Astronomer Royal at Greenwich. We can see Flamsteed House, the original buildings of the observatory in the background there, sort of as if they were his gentleman's estate in the country, in the park. So he's connecting himself closely with that, naturally. In his hand, he's holding a diagram of the prismatic micrometer for an achromatic telescope that he designed, and something that he had published in the Philosophical Transactions of the Royal Society. So an instrumentalist, an innovator, someone connected to the Royal Society, of course. And his hand there is resting on something perhaps even more important, which is his observations done at Greenwich. And that was something that really he saw as his most significant legacy. He was the first Astronomer Royal to publish while he was incumbent in position, so while he was alive, and he made sure that he did so in a regular fashion. And he also spent quite a considerable amount of time trying to gather and deal with, and in the case of James Bradley, publish observations of previous Astronomer Royals as well, to make them useful, to make them public, make them accessible to those who wanted them. So I won't give a full biography, but his institutional history, looking back to that previous slide, was Westminster School, where he was at school, Cambridge University, then the church. He was ordained, he joined the Royal Society, and then he joins becomes Astronomer Royal at the Royal Observatory. And there, institutionally, he's also dealing with, among other things, the boards of Longitude and Ordnance and the Admiralty, so those different sort of branches of government. So rather than stargazing, the astronomy he was involved in was more about this kind of thing, the Maskelyne's astronomical observations. You can see those volumes, his legacy there in the middle, and also the nautical almanac produced from those observations, which I'll say more about as I go along. But again, it's about making this data regularly available to the different publics who might be able to use it. So it looks like this. It's undertaken in places like this. These are the Meridian buildings at the Royal Observatory in Greenwich. If you ignore the buildings to the left-hand side, you've got a kind of recreation of what the observatory was like under Bradley and Maskelyne after him. So you have the slots obviously for the instruments set up to observe on the Meridian. For a while, my office was in that building above the Black Door, which was a rather nice place to be and a good view. So I rather miss it. But also, and what I'll be saying more about as I go along, it's being undertaken in places like this, but also in temporary or moving observing kind of spaces like on board ships or in portable observatories like the Tents observatories you can see here from images linked to the voyages of James Cook, which again I'll come back to. So the chief project of 18th century astronomy, and underpinning all the others that I'm going to be talking about, is of course Meridian Astronomy, undertaken in fixed observatories like Greenwich in the 18th century, and with instruments like these. So here's the mural quadrant at Greenwich in the Meridian building, and also images of zenith sector that Maskelyne brought to Greenwich, and on the right, the transit telescope that he inherited from Bradley alongside the astronomical regulator by George Graham. So those were the essential kit, as it were, of the day-to-day regime there. So the Greenwich buildings and instruments, obviously one can still see and visit. They were things that were, as I mentioned, paid for by the British government. They didn't vastly fund the observatory in the 17th, 18th or 19th century, but it was funded, and they did so because they were persuaded of the practical benefits of this kind of work. For those undertaking the work, I think there is inevitably an element of knowledge for its own sake, and indeed a sort of pursuit of accuracy and precision for their own sake, I think. Certainly you get sort of degrees of precision that are, you know, far beyond what might be needed to support navigators at sea, which is the principal founding mission of the Royal Observatory, and one that Maskelyne very much reinserted. But nevertheless, the practical projects are absolutely there, and I'll be talking about some of those and what they were meant to achieve for the kinds of people who would support this kind of these projects and this kind of observation, whether monarchs or governments or private interests. So what am I talking about? I'm sure many of you are already aware of many of these kinds of projects, but what I want to talk about is the way that they're very interlinked and have overlapping locations and instruments and personnel involved with them. So they are particularly mobile, and indeed, as the title of the talk suggests, global projects as well. One of them, and has already been mentioned earlier before we went live, I think, was the transit of Venus. So the desire to measure solar parallax and to thereby establish the astronomical unit, as it's called now, the distance between the Earth and the Sun. And that was mobile because in order to observe it, you have to get around the world to where it is most visible, and indeed, you want to observe it from different locations on Earth so that you can get a decent measure of parallax. You've got enough distance in the observing positions that you're in to make that a viable observation. Stellar parallax was also something that had been pursued earlier and continued to be pursued. And could be observed, or well, could be attempted to be observed in all kinds of location, but it was still something on the agenda, and it does get linked into the kinds of expeditions and mobile observations that I'm talking about. So that's essentially the question of how far away are the stars, and do they appear to move as a result of the Earth's motion in orbit around the Sun. Finding longitude at sea, a core project, of course, that is core to the foundation of the observatory at Greenwich and in Paris and other places. And in the middle of the 18th century, it's something that's coming into fruition, in particular through the development of the lunar distance method, and also sort of concurrently the timekeeping method, which also involves astronomy and observers, and the regime at Greenwich as well. The questions about the shape and indeed the makeup of the Earth were also very current, being pursued both by gravimetric observations, so trying to understand the gravitational influence of different parts of the Earth, whether that's sort of small local features like mountains, or if we're talking about the shape of the Earth as to whether it is prolate or oblate, as Newtonian theory suggested. So is it sort of pointy, as it were, or was it kind of slightly flattened at the poles? And that was also pursued through survey, through triangulation, so trying to establish whether different sort of degrees of latitude were a different length at different parts of the Earth. And finally, and more broadly, is survey, which relates to many of these, but I'm thinking about land survey and also hydrographic survey. The role of astronomy is most key in terms of fixing base positions for surveys accurately on land, whether that's a sort of coastal survey coming off that, or land surveys. And also, of course, the sort of interlinked disciplines of observational techniques and instruments for more mobile surveying, so whether that's with theodolites or whatever. So all of these projects were very much based on the catalogues of stars and tables of motions produced in static observatories like Greenwich. Several of these projects also have reciprocal relationships with that data, so it's based on it, but it was also helping to improve it. All of them begin with observations designed to fix position as accurately as possible. So that's using core sort of suite of instruments, clock, portable transit instruments, astronomical quadrant, reflecting telescope, in order to establish local time, for example, through observing equal altitudes, by establishing longitude, perhaps by observations of Jupiter's satellites, and determining latitude by observing the height of the sun or stars above the horizon at particular times. So some of these projects obviously seem practical enough to be of general and inevitable interest to government bodies like the Ordnance, which was the institution that funded the Royal Observatory in Greenwich in the 18th century, and also the Admiralty, which was associated with the Board of Longitude. Things like navigation, finding longitude at sea, and survey, whether of coasts or land, are obviously relevant to undertaking overseas trade. They're relevant to the military and strategic interests, and more broadly, the development of empire. The question of the shape of the Earth perhaps sounds a little bit more esoteric, as perhaps do the questions about parallax, but they were, again, very relevant to these kinds of more practical questions, and they were certainly sold to funders, to governments, to monarchs in this way. They were sold as being a way to improve astronomy, which is a way to improve your charts and your tables, astronomical tables. They are a way to establish the comparability of observations at different places. They are a way to improve the theory. So transits of Venus observations were seen as a way of plugging in much more real as opposed to relative distances and sizes of the Earth, Sun and Moon and so on into Newton's sort of gravitational formula as a direct payoff to understanding and improving lunar theory, which was, you know, a sort of core thing for the early 18th century and onwards indeed. So trying to solve the complexity of the three-body problem that had really foxed Newton, so that his lunar theory was never really established. Stellar parallax, perhaps a bit less directly related. It was something that would essentially confirm what was already known, that the Earth goes around the Sun. And it was something that was seen as a kind of a missing element of knowledge, this kind of giving an idea of a real sense of place in the universe and distances involved. Perhaps for many a sort of purely scientific and curious kind of question rather than practical. But it certainly was of interest to patrons for more pragmatic reasons. Some of them were about, you know, being able to prove the real capabilities and prowess of your observers and their instruments. Particularly, it's a very difficult thing to observe. So if your instruments can observe it, that means they are really good. And there are then elements of national pride and sort of international competitiveness coming into that sort of thing. Being able to demonstrate success and observing something like stellar parallax could be an important coup that a monarch would like to have, for example. So back to Maskelyne and his biography. He was certainly clear when he was writing about his own life in retrospect that astronomy was his passion, and that he wanted to develop a career in this area if he could. Not an easy thing to do in the 18th century. He talks about how his sort of first introduction and sort of moment of realizing how much he enjoyed astronomy was observing, I think it's 1749, there was an eclipse of the sun that he observed. And that combination, I guess, of the phenomena, but also, I'm sure for him as a mathematician, and that's where his sort of real capabilities lay, understanding that you can use mathematics in order to predict this happening, I'm sure really captured him. He certainly needed to work for a living, particularly early in his career. And his first paid positions were a fellowship at Cambridge, so there he is as a mathematician, but also as a curate in Shipping Barnet, and that was his main work essentially at that period. But all the time he was using his connections at Cambridge and elsewhere to keep connected in with the scientific world and to try and find his way into it. He managed, possibly through John Bevis, who has an observatory in Stoke Newington, not too far away from where Maskelyne was at that stage, and was a fellow of the Royal Society, or possibly through other mathematicians and astronomers based at Cambridge that he remained in contact with. Either way, he managed to get an introduction to meet James Bradley, then Astronomer Royal, at some point in the 1750s. And that really allows him to get it into this world. In 1758, when he's 26, he was elected Fellow of the Royal Society. So he worked with Bradley. He was able to use his mathematical skills to do some calculating work for him, processing some of the observations made at Greenwich, and also probably assisting with work on lunar theory, both Bradley's work and also work of Tobias Mayer, which we'll come back to, a much improved lunar theory that ends up being very significant for the question of finding longitude and for Maskelyne's career. So that placed him in just the right sort of area, but he also timed this very well because he was able to get straight into a very significant project, both longitude, but also the question of the transit of Venus. So 1761, the Royal Society rather belatedly realised that they might want to take some action in terms of organising expeditions to observe that. Once they heard that the French were doing it, they thought perhaps we ought to be doing that as well. And they rather hastily called on Bradley to help organise something to make sure that there were British interests and observations done as well. So that, of course, to measure the solar parallax, and Maskelyne refers to it later in his autobiographical notes as that great desideratum in astronomy. So backing was forthcoming from the Royal Society and also from the King for making observations of the transit of Venus. And this was seen as for the promotion of a science, astronomy, so intimately connected, and I think this is what's key, with the art of navigation, as well as for the honour of the nation. So those twin things, navigation for building empire, your navy, trade, etc., and the honour of the nation were what someone like George III would really care about. So they put together 2 expeditions, one aiming at, although it never got to, Bencoolen in Sumatra, and the other to St. Helena in the Atlantic. Maskelyne's proximity and already working with Bradley meant that he gained an opportunity to get involved in planning the expeditions, and also allowed him to make the nifty manoeuvre of gaining patronage to help with the expeditions from the Royal Society and George III, who was sponsoring the efforts. And it was a career-enhancing opportunity for him because of his ability to hook the voyage that he was going to undertake to St. Helena onto all of these other projects that I've been talking about. So Bradley, as Astronomer Royal and therefore the senior astronomical figure within the Council of the Royal Society, was the obvious person to advise on the expeditions, how they would be manned and how they would be equipped. And he made this statement at Council in June 1760, quickly able to identify which kind of instrument makers, which kinds of instruments would be needed in order to carry out these kinds of observations successfully. But Bradley was getting on in age, but also was quite unwell at this period. So he delegated much of this task and its sort of its further development to the much younger Maskelyne. That undoubtedly made him one of the obvious choices to be a paid observer for these expeditions. And he also made sure he upped his chances by showing off to the Royal Society his own understanding about what the opportunity could provide. So just the week after or whatever, on the 26th of June, 1760, Maskelyne presented a paper to the Royal Society which talked about a proposal for discovering their annual parallax of Sirius, so looking into that project of stellar parallax. His proposal was that Sirius could be observed at the zenith over St. Helena over the course of a whole year. So not just going to St. Helena to observe the transit on a one-off day, but to spend a whole year there in order to carry out this observation, which he described as being the fullest and directest proof of the Copernican system. This idea of observing Sirius was directly inspired by the observations of that star that were made on another overseas expedition, that by the Abbé Nicolas de Lacaille in the early 1750s at the Cape of Good Hope, where he had gone to observe the southern stars and to map them again as a support essentially for navigation. And we again get this idea of multifunctional scientific expeditions and the sense of what the significant projects were of the period. This very much comes from Lacaille and other continental astronomers who were interested in many of these questions. And Lacaille certainly inspired him in terms of the process for successfully observing lunar distances in order to find longitude, and this project of stellar parallax observation, and also the question of the shape of the Earth, which came into observations made by Lacaille using zenith sector. So this engraving shows the zenith sector, supposedly with Mackay observing beneath it, which he used at the Cape, but this image shows it being used as part of the triangulations across France, which were undertaken, again, sort of multi-purposely to establish a length of the meter for the new metric system, but also is combined with questions about measuring the shape of the Earth. So this kind of combination of projects that's going on for Maskelyne and others means that although, as was always possible, and indeed as was to happen, a transit of Venus observation could be a failure. So at St Helena, Maskelyne was foiled by clouds on the crucial day. He had other ways to prove his abilities and ways to make the expedition into a significant contribution. It turned out, though, that his attempts to observe stellar parallax were also a failure, but he had many other things up his sleeve and other key projects. So one of these, like Lacaille, was about the shape of the Earth, which was both something that he looked into observing potentially through gravimetric methods, so using the rocky places of St Helena to see if the pendulum bob of the zenith sector would be attracted by large land masses, and the question of making observations of the length of a second's pendulum on different parts of the Earth, so using the two different Transit of Venus expeditions to make those observations and see how they compared in different parts of the world. So that was another string to his bow, as it were. And the other one, of course, was Longitude, which he was contributing to both on St Helena by making observations of the moon's parallax in order to feed into the corrections to observations that needed to be made, and also by trying out the lunar distance method during the voyages to and from. So ultimately for this voyage, this expedition, this was his main achievement and the one that really sort of made its legacy in terms of his later career. So this was making use of the lunar distance method based on the lunar tables produced by Tobias Mayer, and using a Hadley's quadrant, what we now call an octant, on those voyages to and fro. And he demonstrated on these voyages that this system could produce useful results. So Mayer's tables have been submitted to the Board of Longitude. Bradley, as a commissioner of Longitude, was looking into them. He was, and possibly Maskelyne helped him, to test their reliability, their accuracy from Greenwich. And then this expedition to St Helena is really sort of the first British trial, as it were, sort of unofficial trial to see how well they might work when actually put to use at sea. So he took these tables and then had immensely long series of computations to do in order to turn observations made on board ship into a reading of longitude. But he showed it could be done, and it was reasonably accurate. This led to him publishing on his return this book, The British Mariner's Guide, which he suggested could be used based on the tables produced by Mayer, and using Hadley's quadrant would allow people to find longitude while they're at sea within a degree, which was one of the levels of one of the lower rewards offered under the 1714 Longitude Act. So it was something that was being aimed at, and he was suggesting this could be done with the lunar theory and the observing instruments that were available at that time. This is something that might perhaps have been part of Maskelyne's future career in terms of a commercial publication. That might have been one of the ways that he could have continued to earn a living working with the observational astronomy and mathematics that he enjoyed. But of course, his proven abilities and interests made him a useful individual for others as well. And the voyage to St Helena gave him a high reputation as an observer to go alongside the high reputation he already enjoyed as a mathematician. And that meant that he was chosen by the Board of Longitude in 1763 to make a voyage to Barbados to undertake trials of 3 different methods of finding longitude on the same voyage. So Maskelyne was to go and make observations with Mayer's tables. So they were under test to see if Mayer deserved a reward posthumously. Sadly, he died before he could be personally rewarded. He also made observations of Jupiter's satellites, or some at least, on board ship, using another method, which was a marine chair designed by one Christopher Irwin, which was meant to stabilize an observer enough to allow them to make that very delicate observation of Jupiter's satellites while on a moving ship. And also under trial was Harrison's Sea-Watch, now known as H4. So Maskelyne made observations for 2 of those methods, and he was to make observations on Barbados in order to establish properly what its longitude was, in order to compare these different methods against. This again proved for him and many others the potential of the lunar distance method. It got it continued to get good results, and indeed better. So we have here a sextant. So this is early days in the use of the sextant rather than the octant, which allowed a greater degree of arc of observations, and also these are more precision instruments, so more accurate observations, and that helped increase the possible accuracy to be allowed with the lunar distance method. And also the Voyage established Harrison's Sea-Watch as potentially very accurate indeed, well within, indeed both of them, within the realms of the highest reward being offered under the 1714 Longitude Act. Maskelyne dismissed Irwin's marine chair, and that was not a viable method as far as he was concerned. He returned with these results to the Board of Longitude, and he also returned to learn that Bradley's replacement as Astronomer Royal, Nathaniel Bliss, had unexpectedly died while he was away in 1764. And he was, of course, ideally placed through his experience on this voyage, the St. Helena voyage, his connections at Cambridge in the Royal Society, and indeed some other patronage as well, that he was incredibly well placed to take on the role of Astronomer Royal after Bliss's death. So in that role, he became ex officio Commissioner of the Board of Longitude, which took up a lot of his working time thereafter, and also essentially ex officio on the Council of the Royal Society. And he continued to take a close interest in the development of these methods, the timekeeping and astronomical methods of finding longitude, and extended into advising on a number of other astronomical and scientific matters. He made the work, as I suggested earlier, of the Royal Observatory regular business, focused on that original mission of the observatory of undertaking astronomy in order to improve navigation, with his regularly published outputs of the Greenwich observations, and in particular the Nautical Almanac, which was paid for by the Board of Longitude, but absolutely based on observations at Greenwich. This slide is a kind of composite to say all the work of the Board of Longitude that Maskelyne was involved with, both very promising methods like the timekeepers of Harrison, and also makers like Larkham Kendall, Thomas Earnshaw, and John Arnold after him, which sort of together produced what became the marine chronometer within Maskelyne's lifetime. Also a number of somewhat less plausible methods illustrated here, but I've included these just to make the point I'll come back to at the end, that the papers of the Board of Longitude were digitised as part of the projects that I was talking about at the beginning, and are available for perusal, and well worth time if you're interested. So as a Commissioner of Longitude, as Astronomer Royal, he was advising the Admiralty on astronomy and navigation very broadly, although he himself never made an expedition overseas again. But he is remembered for his expedition to Schiehallion, making observations not at the peak here, where I was myself last summer. I finally managed to climb it on a beautiful sunny day. I should have included my pictures, which are much bluer skies than this one. So, yeah, making observations on either side of the mountain of Schiehallion in Perthshire in order to establish the attraction of mountains, the project of so-called weighing the world. So this is his contribution to that question about understanding the shape and density of the Earth by measuring gravitational attraction either side of this conveniently sort of shaped mountain, relatively sort of symmetrical in shape, and setting up a zenith telescope on either side in order to see if the plumb bob was being attracted by the mountain itself. He undertook that with the same zenith sector that he used on St. Helena, which had been adapted and corrected. So his problem observing there had been down to a fault in the way that the plumb bob was suspended. He had that corrected, suggested with being able to show that he could make these observations that he had now created or helped produce a really accurate instrument and a whole regime of observing that would be truly reliable. He did that alongside the use of one of the astronomical clocks that were used on the Transit of Venus expeditions made by John Shelton. And the one he used there is the one that's now on display in Chambers Street at the National Museum of Scotland. So he measured a deflection that he established as being caused by the mountain of 5.8 arc seconds, and he presented these results back to the Royal Observatory as confirming Newtonian theory about the mutual attraction of bodies, and also the comparison that was made, the calculation to establish the density of the mountain in relation to a mean density of the whole Earth suggested that the core was denser than the surface, disproving theories that some put forward of a hollow Earth. This was work that Maskelyne did with others. He won a Copley Medal for it, but he was very much relying on the work of Reuben Burrow for the survey that was done of the mountain itself in order to establish its physical nature, its volume, its surface and so on, and the calculations carried out by Charles Hutton. So both of those individuals linked to the Office of Ordnance made this work possible. And they, between them, calculated the density of the mountain as 2.5 times that of water, and that of the whole Earth as 4.5 times, which is rather lower than the figure we would get now. It's 5.52 times the density of water, I believe. So he showed off through this project the accuracy of his instruments and his observation and his process of observing, which required a vast number of observations and a rotation of the instruments in order to cancel out possible errors and so on. It also had its practical outcomes, potentially, showing that land features like mountains certainly could have an appreciable impact on observations and potentially on the length of a pendulum needed to beat seconds and timekeepers as well. And these were things that would need to be taken into account in order to produce the most accurate possible positional astronomy and cartography as well. And beyond that, can extrapolate to different locations on Earth in relation to the shape of the Earth itself. So the Schiehallion experiment is one among a long series of complex investigations by continental astronomers, Maskelyne and others, into this question of the shape and structure of the Earth that did have directly practical implications. So as I mentioned, Maskelyne didn't himself go on overseas expeditions again, but he was already, before the Schiehallion expedition, playing a very crucial role in developing the precision side of voyages of exploration, those of James Cook in particular, but also other voyages that came after and were modelled on that. Those now being led by William Bligh and George Vancouver, John Constantine Phipps, Matthew Flinders, and others. And also, very crucially, Maskelyne had an impact on the astronomers who accompanied them on these voyages. So the first occasion that he again gets involved in this, not surprisingly, is the next transit of Venus that took place in 1769, and most famously was observed by the British at Fort Venus in Tahiti as part of Cook's Endeavour expedition. Given Maskelyne's experience, personal and also organisational experience from the 1761 transit, and that he was now, of course, Astronomer Royal himself, it's not surprising that he was the key figure in organising the observing efforts, so the astronomical elements of the Endeavour voyage, but also the other expeditions that took place by the British. So there was Cook and Charles Green on Tahiti, but also expeditions that went to Norway, to Hudson's Bay, to Northern Ireland, and to the Lizard in Cornwall. So he was key to organising the instruments that would be taken, selecting the observers who would go, and selecting the observation sites. Once again, George III granted funds to allow the Royal Society. Not only was the Admiralty allowing them to use ships, or the East India Company helped out as well, but a grant of funds was made to allow the Royal Society to buy 5 sets of equivalent suitable instruments. And they, together with instruments that were one way or another acquired by the Board of Longitude, provided a really important resource. They were the hardware that trained observers could make use of, not just for these observations in 1769, but also for a range of observations on these voyages and others in the future. So as well as observing the transit of Venus, the astronomers were the observers selected by Maskelyne for the Board of Longitude or the Royal Society were instructed by him to do, well, as much else as they possibly could during their voyage. They were encouraged to test out and to undertake the new longitude techniques, in particular to try out Maskelyne's new publication, the Nautical Almanac, which appeared just in time to go out on these voyages, and to make use of the sextants and so on, and see how well this whole process would work at a great distance to Greenwich or the Atlantic over in the Pacific. So using the Nautical Almanac to determine time and to make lunar distance observations. He also asked them to make precise observations of location whenever it was possible, whenever a ship was basically in a particular spot for long enough to get off the ship, set up an observatory, make a series of observations in order to provide fixed positions against which surveys of coasts could be made, and generally charts could be improved. He also asked them to make pendulum observations, feeding into that question of the shape of the Earth, and a whole range of others of various sorts, magnetic observations using dip circles as well as compasses, and questions about sounding to get a sense of depth of water, salinity of water, and so on. So a whole range of things requiring a whole suite of instruments and series of results to be published afterwards, which again, Maskelyne largely oversaw. So this process of having the right instruments and the trained observers on board a ship going abroad might have been a 1769 one-off because of the astronomical event to be observed of the transit of Venus. There was no essential reason to include an astronomer on subsequent voyages, but the success of Cook's voyages, the success of the observations that were made both the kind of natural history collecting that went on. We had Joseph Banks on the Endeavour voyage as well, and that took a great deal of interest, but also the more physical observations as well, and the production of charts and so on were impressive, and they gave real impetus to this process. And it gave Maskelyne the opportunity to send out other astronomers again. So when the next voyage of Cook was being planned in 1772, Maskelyne took the opportunity to write to the Earl of Sandwich, John Montagu, who was also First Lord of the Admiralty, to say, let's make the most of it. As this quote says, he was suggesting that the expedition that was planned would be rendered more serviceable to the improvement of geography and navigation than it can otherwise be if the ship is furnished with the astronomical instruments as this board, that's the Board of Longitude, hath the disposal of or can obtain the use of from the Royal Society. So that's really making use of the previous transit of Venus instruments. And also he suggests some of the longitude watches. So this was the copy of Harrison's Sea Watch that was made by Larkham Kendall, also some watches made by John Arnold. So he was very keen to have the timekeeping method of finding longitude being trialled alongside the lunar distance method. And he says, above all, if a proper person could be sent out to make use of those instruments and teach the officers on board the ship the method of finding the longitude. So he wants well-trained observers there, but also to have them act as teachers to try and get instruments and methods like this embedded, at least within, a well-funded kind of high-status voyage like this. So I think this is quite a crucial moment, and it does succeed in making Maskelyne integral to the activities of those series of other voyages in the later 18th and early 19th century, funded by the Admiralty, and including a whole range of scientific observation as part of the work that they did. This is probably unreadable on screen, but it's very typical of a draft list drawn up by Maskelyne of the sets of instruments that should be taken on voyages like this. This is the one of instruments delivered to Cook for the third voyage, but there are very similar ones for the subsequent voyages as well. And essentially leading towards a kind of standardized essential kit of how to carry out precision exploration, as I've termed it, the kind of mobile, portable observatory set of instruments, the clocks, the sextants, the astronomical quadrant, and so forth. And also the books, under the line at the bottom is got a list of books, which include tables requisite, which was the supporting volume to help use the various, again, got a list of which nautical almanac years should go with them, and Mayer's tables themselves as backup. So you've got a whole library of astronomical texts to go out with these astronomers as well. So you get this kind of regular suite of instruments that is used, and then alongside that a range of instruments for those other kinds of observations I mentioned, and also instruments that might themselves be under trial. So the Board of Longitude might be interested to see how a particular compass that was newly invented would perform on a voyage. So those might be sent out alongside, again, making use of these trained observers. So Maskelyne established this suite of instruments. He selected the observers. He helped to train those that he hadn't already worked with one way or another. He stipulated their books, their equipment, the instructions that they took out with them, and continued to support, without himself traveling, the prosecution of all of these kind of global and mobile projects. And alongside this, he was also helping to support the careers of these observers and mathematicians that were sent out, although perhaps only for a period of time. These were very piecemeal careers for people. If you didn't get to be Astronomer Royal, and there was only one of those at a time, it was kind of difficult often to put together enough different pieces of work to make a career. But if you had Maskelyne with you, it was a possibility. So these were people who were variously observers on voyages like this, funded by the Board of Longitude, or they might be computers for the Nautical Almanac, or they might spend time as assistants at the Royal Observatory in Greenwich. So essentially just wanted to finish there, saying that really I think Maskylyne's key contribution is this support of the ongoing observation for all of these sets of projects of 18th century astronomy, getting these trained observers onto naval voyages with precision, high-class instruments, as supported by the data that he produced at Greenwich, Greenwich observations and the Nautical Almanac. Just to finish off, this was the digitalisation I mentioned. Cambridge Digital Library has got some papers of Maskelyne, both from Cambridge and also from the National Maritime Museum, have been digitised and are included there. There's also all of the papers from the Board of Longitude that can be perused. All of the minutes have been transcribed. The other ones have been described variously, but aren't sort of word searchable, as it were. Various essays and so on that may be of interest as well. So if you Google Cambridge Digital Library, you should be able to find it. And just a little bit of further reading, including books that I've worked on, and the URL there for the digitalisation. So thank you very much.
Thank you, Rebecca. That's fascinating. Before we get on to questions, can we thank Rebecca for a talk, please?
Thank you.
As usual, if you can, if you're on Zoom, put into chat that you want to ask a question, and we'll get you to read it out. And if you're on YouTube, please put your question in the live chat there as well, and then we'll read them out. Okay, Peter, are you there?
Yep, I'm here.
Want to read out questions?
Yeah, we've got one for Ian. Ian, do you want to ask your question yourself? You are there somewhere, aren't you?
On that last slide, the list of instruments, I noticed that at the top it says belong to the Board of Longitude, but it's been scored out. Is there any significance to that?
Good spot. Sorry, I'm just bringing it up for myself again. It says, belonging to the Board of Longitude, and I think it is then scored out, and he adds in delivered to Captain Cook. So I think it's a list of what they have potentially to go out, and then it's a list of what is actually in Cook's hands. It's not the only version of that list, so there would be others to compare it to. At the digitalisation, would be interested to see, where that correction came in.
Yeah.
But I think that's what it is.
Okay, next question is from Andrew.
Thanks, Rebecca. That's fascinating. I just wondered if Maskelyne's role in producing the sort of tables for the lunar method and then been on the board that helped decide which method was the best, did it prejudice him in any way against Harrison, or was he a true scientist and said which gives the best results?
I think the idea that there was a sort of a conflict, I mean, obviously there was for Harrison. He said, I've produced this thing, it got you the results you've wanted, give me the money. The Board of Longitude said, yes, but there's just one of these. Could anyone else ever make one? Could you make another one? Is it a viable method that we can roll out? So they were holding back, seeing this as a fulfillment of what they asked for, which is a sort of practical, useful method at sea. The astronomical methods were, in a sense, easier to roll out. And the main point is they were complementary. From their point of view, it's not this one wins against this one. It's we want to fund both of them. We want to use both. And essentially, they were both used. You always want you want as many methods as you possibly can. You would continue to do dead reckoning alongside using astronomical methods of one way or another. Maybe not every day, all the time, but using them as a check on where you're going. Alongside having a timekeeper. And until you've got enough timekeepers to have, say, 3 on board a ship to know how well they're working, you can't rely on them on their own. So if your watch goes wrong and stops, you will always need astronomy to reset it, as it were. So the Board of Longitude essentially doesn't pick a winner. It supports both by giving Harrison personally a lot of money, and ultimately he does get more than £20,000, which is the top reward, but also by putting a lot of money into the publication of the Nautical Almanac. So that is funded a great deal as well. For Maskelyne personally, yes, he's interested. He doesn't personally expect to get a reward. He publishes that book saying, you know, this does enough in a sense to get at least half the reward, but he never suggests it's a claim. He never takes that to the Board of Longitude before he's a commissioner. Essentially, it seems that commissioners feel that they're not eligible for rewards, but also astronomy is such a collaborative effort. You can't really give that reward to one person because it relies on the work of so many. So I think he finds it he found it a lot easier to understand the method he's familiar with. He understands how it works. He can see that it's readier to roll out. He wants other people to do it. It was considered potentially the more accurate if you make repeated observations in good conditions than a one-off timekeeper. So for all of those reasons, he always felt, and because it's the underpinning fundamental thing to see if your clock's working, that was always the one that he would wanted to see being rewarded. But he absolutely supported the investigations into the timekeeper method as well. He, as that letter to Sandwich shows, he wanted to put them on board the voyages to see how well they performed. He encouraged Kendall, he encouraged Earnshaw and others to, you know, continue their work as well. He undertook many trials himself of those timekeepers at Greenwich, not always in the way that the watchmakers themselves wanted him to. There was sometimes a disconnect of understanding the technology and the processes, but he absolutely was invested in that as well.
I'm aware that poor old Harrison, in his nearly 17, had to walk to London about 250 miles to go and claim his money.
I don't know if he had to walk to London. He was living in London for a start. He was in Red Lion Square by then. I mean, Harrison had, you know, he did pretty well. He was, you know, he got quite a lot of money. So I could go on. Sorry.
Yeah. Thank you very much.
We've got one from Graham. Do you want to ask your question, Graham?
Yeah, you'd mentioned that when on a voyage, he could have trained people how to work all these instruments. Now, having seen how some of these instruments are, they're very complicated. And even just how to work all the calculations is not straightforward. How did they have a sort of system for training mariners in the Navy or merchant Navy of the time to learn how to work all these different systems? Or was it just sort of ad hoc, here's a book, here's an instrument, go and work it out?
It was rather ad hoc before, you know, into the 19th century when it became somewhat more normalized. It was very much a sort of private world of, you know, you could get yourself a sort of private navigation teacher if you wanted. You could improve yourself this way and show that you could do X, Y, and Z. It was a real struggle, not surprisingly, to get, you know, mariners who already knew how to get around. You know, they navigated to their own satisfaction to take up new methods, and particularly ones that were, as you say, complicated. And the mathematics is reasonably hard and certainly very boring to do. And it was very hard to get that to being part of the general work of ordinary navigators. And lunar distances probably never were a very serious part of more regular voyages. They were absolutely used on these more elite scientific voyages. They were potentially used by East India Company at crucial parts, making decisions about their quite complicated routes. But people weren't, you know, falling over themselves to do it. It worked, I think, where you had someone, you know, like an astronomer like Charles Green on board a ship with, you know, a reasonably keen, interested kind of officer who might want to pick it up. So there is clearly someone like William Bligh is on the Cook voyage. He learns directly from Green. He takes that forward. So you get those kinds of instances. You get this being taught in some of the more elite schools, the Royal Mathematical College, the Royal Academy at Portsmouth, and these astronomers are precisely the people who go and teach at those schools. So you've got the name's just gone out of my mind. William Wales, for example, ends up as a mathematical master there. So you've got some individuals being trained in these more complicated methods, but that's by no means the general population. From the early 18th century onwards, mathematicians were put on board ships as schoolmasters who were meant to train the midshipmen in making these observations. There is debate as to how effective that was or how often they were put on board. Certainly there were quite a large number of them trained and paid, but how willing their pupils were and how advanced it might have got mathematically is a question. So it was tricky, frustrating. Maskelyne was always trying to make it something that, say, masters had to do. They had to get certificates, and that never quite came in during his lifetime.
And last one from John Morrow.
Yeah, it's probably possibly a little bit of an unfair question. All these astronomers got deposited on an island that they didn't really know the longitude or latitude of, and they then somehow determined what the correct time was, because they used that to regulate their clocks, and obviously that happened in all these expeditions. And I just wondered how they ever determined what the correct time was when they didn't know really where they were.
Yes, I mean, you can. Some of you can probably answer this better than I can. I mean, certainly whenever they set up and establish, they're making that whole series of observations, equal altitudes and Jupiter satellites and so forth, and trying to get as good a fix as they can of the longitude and the latitude and the time. But as you say, there is a sort of reciprocal nature to those. I'm not sure I could talk you through the process and just how accurately they managed to do it. But they were getting results that were not far off, and certainly the kind of surveys that Cook was doing, some of those charts remained the data for those parts of the world right through until we've got satellite navigation going up.
I was thinking when Harrison's clocks were taken out, they arrived on land and they then checked them and said that they're within a few seconds or something. So they managed to determine the local time quite accurately.
I mean, so that's what Maskelyne was doing on Barbados, was establishing just where Barbados was in order to see if Harrison's clock worked. And that's because they had utterly failed to do that on a previous trial to Jamaica, when they realized only after the events that they didn't really know where Jamaica was. I mean, they are absolutely in the process of fixing the world at this time.
Okay, thank you.
Back to you, Mark.
Okay, Will, I think we have a question on YouTube. Is that right?
Yep, just the one question. Excellent talk, Rebecca. Everybody enjoyed it. Got a question from Brian Morella. And what was the precision of navigation, location determination for Royal Navy before and after Maskelyne's work?
Oh dear. I've written down a whole series of how accurate it was there, and I'm not sure I've got a very clear answer for that. I mean, what the Longitude Act was looking for was, so its top reward was for finding longitude within half a degree. So that works out as about 30 nautical miles. And I think for timekeepers, that's an accuracy to about 2 seconds a day, which was what was achieved or bettered by Harrison's timekeeper. That's what lunar distance could achieve in good result. I mean, with the sort of basic tables, you've got sort of Maskelyne was managing to achieve it certainly within a degree of longitude and sometimes within half a degree, and that got better as the theory got better and as the instruments got better as well. So this is, by no means only Maskelyne's work. This is, instrument makers and mathematicians and astronomers all working together. I think the best sextants could kind of measure to within about a sixth of an arc minute. So they themselves, will determine the accuracy that you're going to achieve. And you've got sort of errors, within half a degree of longitude just in the nature of the process. So if you add all that up, you need to do these repeatedly, and they're not going to pinpoint you, absolutely on land. If you're doing these observations on land, you're always going to get better results. And if you're doing them, with a precision instrument rather than a handheld sextant, again, you're going to get a better result. But certainly, I think you were getting a sort of accuracy after 1800 to sort of within a tenth of an arc minute with your sextants. And again, all of these things improving. So incremental and very much about this combined sort of work being done by all the different people involved, from including the observers themselves, and how used they were to doing these.
Excellent. Thank you very much. It's all from me. Thanks, Mark.
Okay, thank you. Before we move on to Alan Slot, can I just ask a more general question? So obviously there's a lot going on in Greenwich in the 18th century, but in Scotland it was still quite early days. There's Clorin in Edinburgh, and there was Gregory in St Andrews. But you say astronomy is very collaborative. Was there much collaboration between England and Scotland at the time? Any communication even? When I know there was a bit of a Jacobite situation going on in the mid 18th century, so that might have confused things a little.
Sorry, I got distracted by that question about how our minutes relate to distance. Sorry, so you're asking about collaboration between England and Scotland?
And Scotland, sort of 18th century, yeah.
Yeah. Yes, there is, as you say, a situation, but equally the sort of much of the scientific effort in this world is very much at the sort of the British government. If we think about William Roy's military map of Scotland being done in the sort of 1750s, this is, sort of about British, English army sort of over, taming the Highlands. The Lowlands may be very much on board with that. I think many of the Scots that Maskelyne dealt with, and there certainly were individuals who, might come from Scotland down to London, who ended up being, say, Norse Almanac computers, or potentially assistants and so on. I think politically wouldn't have been sort of had a problem. They were unlikely to have been on that side. What there is, of course, is a huge amount of warfare between Britain and France going on through all of this period. You get collaboration over things like the transit of Venus, but obviously also intense competition about who can get to which parts of the Pacific and who's going to lay claim to different locations. So it's an interesting story of often men of science collaborating despite their differences, but also doing it because they do want to serve, their own governments and monarchs. So, I think that probably hasn't essentially changed. That kind of collaboration and competition remains in many ways.
Great, thank you. Better not to open too many old wounds there, I suppose. Can we thank Rebekah again, please? Thank you. Okay, Alan, over to you. So we're going to have What's in the Night Sky in January from Alan Pickup.
Yep, I'll try and share my screen. Do you see that?
Oh,
yes, we got that. Thank you.
Sorry, get rid of that, and I'll bring up my control screen, which is there. Okay, I'll go back to the slide I showed previously. That's, of course, the James Webb Space Telescope. It was major news over Christmas. In fact, the successful launch of the James Webb Space Telescope took place on Christmas Day. In my case, while our turkey was in the oven. Since then, it's been going very well. Its large sun shield has been deployed, and also its secondary mirror, this device on the end of these 7-meter struts, has been deployed. And as of early this evening, I've heard that the first 3 hexagonal mirrors on the side of the telescope are also successfully deployed. The other 3 on the other side will be put into position starting about 2 o'clock our time tomorrow. That secondary mirror is 0.74 meters in diameter. The main mirror, of course, once it's fully assembled and fully orientated, is 18 hexagonal mirrors with forming a 6.5 meter primary. The JWST is now, as I think I checked just before the meeting, 72% of its way out to its vantage point at the L2 point, opposite side of the Earth to the Sun, 1.5 million kilometers from the Earth, far beyond the moon. It's moving more slowly now. It'll take another 2 weeks to get to the L2 point. And it's still being photographed. 3 days ago, I saw reports of being a magnitude 14. It will be a little bit fainter by the time it gets to L2, but with the sun shield facing the sun and therefore facing the Earth, we can perhaps look forward to some glints and reflections from it, which may make it a good deal brighter than that magnitude 15 or 16. There's the star chart for January, a negative version of the one that appears on Society's webpage. I'm again showing it as a negative with white stars on a black background. I always pick out a few features. The plough is now starting to climb up in the northeastern sky. On the opposite side of the pole is Cassiopeia. We're starting to see Leo coming up in the east at this time in the evening, which is 21:30 or so, sorry, 20:30 GMT tonight. But the main feature, of course, in the sky in January, night sky in January, is the constellation of Orion. We have one planet in the sky at this time, Uranus, just about visible, or visible through binoculars. And also on the chart, I've plotted the radiant for the Quadrantids meteor shower, but I realize that the meteor shower is over by now. We don't have any more quadrantids to see, but I will mention it again as we go on. Let's look at the sun. This is the ephemeris for the sun for January, showing its times, it rises and sets, and also the times of evening twilight. We're losing about 30 minutes of effective darkness in the evening and in the morning during the month of January. But also on the 4th of January, the Earth was at its closest to the sun in the Earth's annual orbit. It's 147.1 million kilometers from the sun, which is about 5 million kilometers closer than it will be at aphelion, its farthest point, on July the 4th. Here's the moon and its phases for the month. We're coming up to first moon in first quarter, so it's visible in the south in the evening sky. Full moon occurs on January the 17th, and then we're back to new moon on the 1st of February, the beginning of February. Eclipses, well, we had one eclipse in December, which was visible from Antarctica, areas around Antarctica. This is one view of an eclipse expedition with the eclipse moon visible. It was, and that's the photograph they took of the diamond ring, if you like, on the moon, and the diamond ring on the edge of the sun, caused by the moon occulting all but a tiny fraction of the sun's disk. You can see that the corona of the sun surrounding the moon's black disk. The eclipse was also observed from space. This was an image taken about 5 minutes before the moon's umbral shadow, the densest part of the Earth's shadow, left the Earth, the shadow falling over Antarctica. This was taken by the Discover spacecraft, the Deep Space Climate Observatory spacecraft, which is located at the L1 point, the opposite point to the L2 point where the JWST is headed. The L1 point lies 1.5 million kilometers from the Earth, and so it's beyond the moon's orbit, but in the direction of the sun. And the moon, you might expect to be in this shot, but in fact, it's off this shot to the bottom. The camera that took it is EPIC, the Earth Polychromatic Imaging Camera. Incidentally, there are 4 eclipses in 2022, 2 of which are visible from Edinburgh. There's a total lunar eclipse at sunrise on May the 16th, and there's a partial solar eclipse visible on October 25th, but with only 19% of the sun's disk obscured at about, well, just before 11 a.m. BST on that day in October. This is the view of the equatorial region of the sky with the sun's position, with the planet's position marked out against the stars for January. The sun is here, and that's its motion during January as it moves from Ophiuchus into Sagittarius. Jupiter and Saturn are being consumed by the sunlight. Certainly Saturn is. That's the relative sizes and appearances of the 2 planets on January the 16th, mid-month. Jupiter is 34 arcseconds in diameter, and Saturn's rings span 35 arcseconds in diameter across from side to side. But Jupiter is magnitude minus 2.1, Saturn's only magnitude 0.7, rather fainter. They're heading into the twilight as the sun moves in their direction. We lose Saturn during the month, but Jupiter is still there, although it's getting a bit low down now in our evening sky for sharp photography. Another planet near the sun, of course, is Venus, which was just visible as an evening star as the year began, but it's slipping through inferior conjunction on Sunday when it passes between the Earth and the sun, though above the sun in the sky, so we don't see it against the sun. We don't see a Venus transit. And then soon after that, it becomes visible as a morning star very low in the southeast before dawn. We also have Mercury, which is not far from Saturn in the sky. It's farthest from the sun, in fact, in the evening sky today. But it stays not far from Saturn as they both slip into the twilight. Mars is low in the south. Where is Mars? There's Mars. Mars is low in the southeast before dawn, very low in the southeast and not terribly bright, magnitude 1.5. And of course, we have those two most distant planets, Uranus and Neptune, which I'll say nothing more about in this talk. If you want to figure out where they are, you need to go elsewhere. Okay, looking north at 20 hours GMT tonight, on January 16th. This is the view looking north with Polaris in the middle of our northern sky, as it always is. It's 56 degrees high for Edinburgh. Its altitude in the sky is the same as your latitude. The sky is turning counterclockwise. So the plough here is beginning to climb in the northeastern sky, tail down or handle down in terms of the saucepan, if you like. Vega is over here dipping down into its low point in the north. I guess it's the brightest star in the sky at these times. Or it's the brightest star in the northern sky. We've got Sirius in the opposite side of the sky in the southeast. And the summer triangle, well, we've lost the southernmost star of the summer triangle, Altair, but the northern ones, Deneb and Vega, are here, and the Milky Way is climbing up in the northwest as it arches up through Cepheus and Cassiopeia and onwards. The view west at the same times, well, here's Deneb and Vega. Cassiopeia now past the overhead point and starting to slip down in the west. The three main stars of Andromeda reaching more or less vertically above the square of Pegasus, which is now tilted on its side. The star that joins the square of Pegasus to Andromeda, of course, is Alpheratz. And of course, the main feature in Andromeda is around there. It's the Andromeda galaxy, M31, which is still well placed in our evening sky. And Pat Diviners has produced that image of M31, the great nebula, great galaxy in Andromeda. Now, I'm looking now in this image or this plot low down in the southwest on January the 8th, tomorrow. The moon is up here, further towards the south, higher in the south, and that's what it will look like close up. Not quite first quarter phase. In fact, tomorrow night it's 40% sunlit, and the first quarter phase occurs on Sunday. But we have a line of planets, Mercury, Saturn, and Jupiter, pointing up towards the moon. Jupiter, that's the shot of Jupiter I showed earlier. So that's brighter than any of the stars in the sky, magnitude minus 2.1. Saturn is a good deal lower down in the twilight, magnitude 0.7. So it's really got past the point at which it's an easy object to observe and view the rings of. Not far away, lower down and brighter is Mercury, which is magnitude 0.7 on the 1st of January and magnitude 1.0 by the 16th of January as it disappears into twilight. In fact, there are 4 little postage stamp images of Saturn and Mercury over the next few days, January 11th, 14th and 17th, as they slide lower down into the twilight. Mercury is relatively close to Saturn here, but it gets further away as they dip down. And you can see from the size of the dots of Mercury that Mercury is getting a good deal fainter. It reaches inferior conjunction on the near side of the sun on the 23rd, and it'll be poorly placed in our pre-dawn twilight during February. Saturn is at conjunction on the sun's far side on the 4th of February, and we won't see it again until late March or early April. This is the view south at a mid-evening time, 20 hours on January the 16th. By that time, of course, Jupiter is set. On that day, the moon is in Gemini, and the Pleiades are quite close to the meridian. They pass 61 degrees high for Edinburgh. But unmistakable in the south-southeast is this glorious constellation of Orion, as the bright star Capella in Auriga approaches the overhead point. Orion's belt, of course, as it climbs in the southeast, points more or less vertically downwards towards Sirius, the brightest star in our night sky. This is looking east, turning east at that same time. Here's the moon to the right of Castor and Pollux, the two brightest stars in Gemini. And here's the Plough coming up in the northeast. And down here, we've got our first sights of Leo rising into our evening sky. If we wind the clock forward to an hour before sunrise on the 16th of January, then this is the view we have looking east, or looking east to southeast, because here's where the sun's coming up, and there is Venus now visible 1 hour before sunrise, very low down, but sufficiently bright that you can't miss it. It's magnitude minus 4.1 on January 11th, and it gets even brighter by the end of the month when it's magnitude minus 4.6. I mentioned the summer triangle was visible in the evening, or not quite fully visible in the evening, but now it's visible in the morning sky, and Vega and Altair here and Deneb are lost behind the picture of Venus. On the 11th of January, Venus is 11 degrees high, sorry, 6 degrees high at sunrise. So it's becoming quite easily visible before dawn. It will soon become visible before dawn. And the other thing to note is that Mars stands well to the right of Venus in the twilight, but it's a good deal fainter, I say at magnitude 1.5. So it's more difficult to spot during the morning twilight. This is the view an hour before sunrise on January the 29th. See, Venus is even higher and closer to Mars, and also visible, not very well on this image, is the thin sliver of the moon, which looks like that on that morning. Now, I mentioned the quadrantids earlier. They peaked on the evening of the 3rd of January. This is the view at 6 a.m. on the 4th of January, when the quadrantids radiant, which was below the handle of the plough, which is just moving off the plot at the top. That's when 6 o'clock in the morning, when the radiant was quite high. So the conditions were as good as they can be for observing the quadrantids meteor shower, with the radiant 70 degrees high at that time. Quadrantids, some of them leave glowing trains in their wake. Here are the data concerning the shower this year. Well, it says it's active until January the 12th, but I doubt very much if you'll notice any particular quadrantids from now until the January 12th. The peak was, I say, on January 3rd, and the evening sky at 21 hours GMT. I looked at it 2 or 3 hours after that point. I saw a couple, including one overhead and about as bright as Capella, and that did indeed leave a train in its wake. The zenithal hourly rate 80 plus means that if you had the radiant overhead, then you might see 80 quadrantids in it if you had a clear sky. But the shower was fairly brief, and by the morning sky, as the radiant climbed higher in the east, the intrinsic rates from the shower were getting lower. Now, during December, the first half of December last month, we had a comet in this area of sky, Comet Leonard, which was tracking downwards towards the eastern horizon. Before dawn, it passed close to the globular cluster M3, which is up here. In fact, it's in the constellation of Canis Venatici, even though it looks like it's between Boötes and Coma Berenices. As the comet passed M3, it made for some interesting astrophotographs showing the comet and the globular cluster together. And one of the best I've seen is this one, which shows the globular cluster M3, and there's the comet. And this strange feature, looks like a feather, is in fact a bright meteor. In fact, it was an early member of the Gemini's meteor shower. The comet, Comet Leonard, at this time was 68 million kilometers from the Earth and 135 kilometers from the Sun. Well, it got closer to the Earth, reaching 35 million kilometers on December 12th, and it reached its closest point to the Sun perihelion on January 3rd, when it was 92 million kilometers from the Sun. But by then it was too far south to be seen from Scotland. In fact, as the comet dived down in our morning sky, it became visible very low down across our western evening sky before it passed near, not far from Venus in the sky, and then continued southwards. In the meantime, as it disappeared from our morning sky and headed southwards, it became more spectacular and developed a nice tail. This is a view taken from California on the morning of December 10th. Well, that's the comet, and this was a Geminids meteor, which peaked a little bit later on, a few days later. By the 21st, well, that's the view of the comet on the 21st. By then, the comet had passed its closest point to the Earth, but we're still getting nearer the Sun. I think you can see it's developing quite a nice tail. The head has developed this bluey-green, quite bright bluey-green glow, which is caused by the dissociation of diatomic carbon. Now, the carbon comes from the organic molecules that are in the ices of the comet's nucleus. As they spill away from the nucleus under the heat of the Sun, they break down, and one of the stages of their breakdown is that diatomic carbon molecules consisting of two atoms of carbon break apart and give out this characteristic light. The light doesn't last very long, so it never stretches very far away from the nucleus, which is right at the comet's head there. So you don't get the same colors along the tail. And as the comet has headed southwards out of our sight, the tail has got even longer. It's reached over 60 degrees in some photographs. This was on January the 3rd, which is one day after perihelion. And you've got the nucleus and the iron tail. This is made up of ionized material, which is being buffeted by the solar wind. Hence, it's not very steady. It's uneven. It's got whirls and breaks in it, because the ions are responding to the magnetic field in the solar wind. There's also a dust tail, and this is the dust tail above the iron tail. It's much smoother and whiter because it's dust and it reflects the light of the sun, so it's more sunlight colored. Anyway, it's still quite a spectacular object for southern hemisphere observers. And if you plot its light curve, well, this is the light curve peaking somewhere between about magnitude 3 perhaps, and it's now fading, and it's expected to continue fading as it's in the southern hemisphere. Now, I've wound the clock forward to January the 16th at 22 hours, 10 p.m. And I've taken out the moon because it's just going to confuse matters. This is the view looking south when Orion crosses the meridian. And I used to call this the Orion hour. And if you look in the do a web search for the Orion hour, you'll still find one or two of my articles that I wrote for The Guardian about the sky at this time when the Orion is in its best position. But because the Earth is going around the sun, this Orion hour happens at a different time on different dates. It's at 22 hours on January the 16th and was at 23 hours on January the 1st. And by March the 3rd, it's at 19 hours in the evening, which is just before about the time of nautical twilight, effective darkness begins. We'll still see Orion for a few more days, a few more weeks rather, after March the 3rd, but it's increasingly westwards and heading up into the sun's glow and twilight. If we use stellarium to display the artwork for the constellations, you can see Orion here, wielding a club and carrying a shield and carrying a sword too, facing off against Taurus, the bull. And overhead, you've got Capella, the charioteer, Gemini, the twins, and Orion's two dogs, Canis Major and Canis Minor, two dog stars, Sirius and Procyon. And then further east, you've got Cancer and then Leo. The equator of the sky is this blue line. This is overlaid by stellarium across the map. showing that Orion's belt lies only just south of the equator. And that means that Orion, the constellation of Orion, is visible from every populous country on the Earth, not just fully visible. It's just not fully visible from the Arctic and the Antarctic. So it's no surprise that Orion has a role in the myths and superstitions that are built up all around the world. We imagine him as a hunter or a giant facing off against charging bull of Taurus. Famously, he has this sword hanging from his belt, and he's got this shield and a club, and the two hunting dogs. And since it was invented by a Dutch cartographer in the 17th century, he's also got a unicorn. What use a unicorn is to a hunter, I don't know. Lepus the hare is scurrying at his feet. There's another original constellation of Lepus, or Lepus, scurrying at his feet, perhaps being chased by Canis Major. If I plot the sun's path during the year, then it arcs above Orion, which means that since the planets and the moon don't stray very far from the ecliptic, the sun's path, you don't see planets against the main stars of Orion. Though you do see them moving through Taurus and Gemini and Cancer and Leo, the constellations of the zodiac. But the club of Orion gets quite close. And in fact, the northernmost bit of Orion gets within half a degree, that's the moon's breadth, of the ecliptic, just around here. And it's close to here, about there, that the sun's position is at the summer solstice. And as an illustration of the fact that planets stay not far from the ecliptic, that's the path of Mars from the middle of 2022 to about a year later. And you can see that around a year's time, in December 2022, this year, Mars makes a backward loop, a retrograde loop in the sky as it's overtaken by the Earth. And in fact, the opposition of Mars comes on December the 8th this year. And on that same day, in fact, and at the time of the opposition, the moon is in the same position, actually hides Mars. So we have an occultation of Mars when it's in opposition at about 5 o'clock in the morning on December the 8th this year, something to look forward to. Okay, what I've done here, back to the Orion hour chart, I've highlighted some of the brighter, messier objects in the sky, all within a range of binoculars. So you can see all these fuzzy bits through binoculars. I'll focus though on Taurus for now. And this is the constellation of Taurus. And of course, one of the features of Taurus is the Hyades star cluster, which is rather closer than the Pleiades star cluster, but they're both open star clusters. And the Pleiades in close-up, Nigel Goodman is shown here. The material that you see around the stars is not, the afterbirth is not part of the cloud of gas and dust from which the star cluster formed. It just happens to lie in the path of the cluster through our galaxy and is being lit up by the stars. It's a reflection nebula. Another famous messier object in Taurus is M1, the Crab Nebula, which lies close to the southern star, the southern horn of Taurus the Bull. And that's the view of the Crab Nebula obtained by Mark Phillips. Of course, this is the debris of a supernova explosion observed by the Chinese and others in 1054. And right at its heart is a neutron star, 30 kilometers wide, that's spinning 30 times a second, and it's emitting radiation like a lighthouse at every wavelength, from gamma rays to radio waves, like a lighthouse. Let's pick a different area to concentrate on. Let's concentrate on Auriga, nearer to overhead. Capella is the sixth, here it is, the brightest star in Cassiopeia. In Auriga, is the sixth brightest star in the sky and the third brightest in the northern half of the sky after Arcturus and Vega. Its magnitude 0.1, it's 43 light years away, and it's receding at 30 kilometers a second. About 200,000 years ago, it was magnitude minus 1.8, which is brighter than Sirius is now, and that time it was the brightest star in our night sky, though there was no one around to observe it, we know of. Capella, the name Capella comes from the Latin for small female goat, and while Auriga is a constellation of the charioteer, the charioteer is often photographed or imagined, I should say, depicted with a goat slung around his shoulders. And he's also carrying 2 kids. These stars here are the kids. And if you look on either side of the line joining Elnath in the opposite side of Auriga to Mahashim, Elnath is in fact the star at the northern tip of the star at the tip of the northern horn of Taurus. Then along at right angles to that line, you have a line of 3 Messier objects which are worth looking for. M36 and M37 are the 2 brighter ones, but M38 is a bit fainter, but all of them lie roughly in a line along the Milky Way in Auriga and are worth looking at. That's M38, M36, and M37, all of them on images by Pat Devine. Back to the Orion hour, I'll focus on Orion itself now. This is it, and one object, which is actually not in Orion, but not far away, is found by taking a line from the head of Orion through Betelgeuse onwards to that star at the end of the arrow, which is 8 Monocerotis, and go 2 degrees or about 2/3 of the length of the belt of Orion to the right, and you have this object, which is the Rosette Nebula, and that was an image taken of the Rosette by Pat Devine. It's also called Colwell 3039. At its heart is a star cluster. The whole thing lies around 5,000 light years away, and the nebula the star cluster is lying in an empty region which is being cleared out by the radiation from the largest stars. One overlooked Messier object, often overlooked Messier object in Orion, is M78, which lies closest to the belt of Orion. Nigel Goodman obtained this image of M78 and a companion nebula, NGC 2071, on Monday night, just a few days ago. M78 is around 1,600 light years away, and it's a reflection nebula. Its dust is being lit up by new stars within it, and the same thing is happening in this NGC 2071, the neighbor. But by far a more interesting area of Orion is the belt and the sword, and I'll look at this. This shows the belt and the sword. Here are the 3 stars of Orion's belt and the sword of Orion with the famous Orion Nebula. Let's concentrate on this region near the star Alnitak, which is the left-hand one of the stars of Orion's belt. And Mike McGovern obtained this image also on Monday night this week of the Flame and the Horsehead Nebula. Here's the Flame alongside Alnitak, and the Horsehead Nebula is a dark nebula seen in profile against a brighter nebula beyond. Looks a bit like a horse's head. In fact, it was first recorded by a Scottish astronomer, William Ina Fleming, in 1888. She was working at Harvard at the time, but she was Scottish born, so we'll claim that one. The sword of Orion down here, well, this was an image taken back in November by Pat Devine of the Orion Nebula, this glorious nebula with a star cluster, the trapezium, right at its heart, and the Running Man Nebula, NGC 1977, further north. I know it's right. The Running Man Nebula, well, there is a sort of outline of a darker outline of a Running Man Nebula seen against the glowing reflection nebula, but the Running Man only shows up in photographs. Of course, with the naked eye, you can see the Orion Nebula as a fuzzy glow, and it's quite obvious through binoculars. So take a look at that. One other area to look at is the region of Gemini and Cancer. Above and to the left of Orion, this is that area in close-up, and one star cluster to look for is M35, which lies at the feet of Castor, at the feet of Gemini. It's 30, I'm looking for the distance, it's 3,870 light years away. And this was an image taken by Ian Smith, M35, and a nearby star cluster. It looks a bit like a globular cluster, but in fact, it's recognized as an open star cluster, NGC 2158. That's much more distant. That's 11,000 light years away. This image is a little bit rotated because in reality, NGC 2158 lies south and west, the opposite side down here of M35. So don't look for it to the left of the brighter star cluster. NGC 2158 is a good deal fainter too. It's only magnitude 8.6, so you're not going to see it very easily through binoculars, whereas M35 is easily seen through binoculars. And Cancer, this fainter constellation of Cancer over here, well, that's got two famous star clusters in it. One of them is M44, or the Beehive, or Praesepe. Horst obtained this image some time ago of Praesepe. 610 light years away at magnitude 3.7. So again, easy to spot through binoculars. On the darkest clear night, you can see it naked eye. And in the south part of Cancer, down here, is M67. That's 2,800 light years away. Magnitude 6.1, more difficult to spot, but it's another open star cluster. Now, before I finish, I'm going to look at 2 or 3 comets. Comet Atlas is visible as it moves in Gemini from near Castor southwards to the feet of Gemini. The comet was discovered in 2019. It's called 2019 L3. It reached perihelion reaches perihelion on Sunday, January the 9th, when it's 386 million kilometers away from the Earth and even further than that from the Sun. It's reportedly about magnitude 9 at present, and Mark Phillips obtained this image on the 3rd of January of Comet Atlas. It's nice to see some comets getting photographed. Another one is Comet Churyumov-Gerasimenko. I can never pronounce it correctly. Our old friend, periodic comet. It's visible in the same area, this time in the northern part of Cancer, but it's fading fast. It's also reported about magnitude 9 at the moment, and it could be magnitude 11 by the end of February. Perihelion was on November the 2nd, and it's about 75 million kilometers from us tonight. And this was a photograph taken by Douglas Heggie a few nights ago. Now, one other comet that no one has in the society, I think, has photographed yet, but they might do soon, is Comet Borrelli, which is a periodic comet, which is perihelion on the 1st of February, and it's moving northeastwards through, at that time, it's moving northeastwards through Pisces into Aries. This is a plot looking south-southwest at 19 hours. So it's a little bit earlier in the evening, and you can still see on this plot the position of Jupiter still above the horizon at this time. Perihelion occurs 198 million kilometers from the Sun. That's on February the 1st. And the comet is receding from the Earth throughout this period. So it's pretty well steady in brightness at around magnitude 9 currently. And it may be a smidgen brighter as it gets towards the middle of this track. So it should be a fairly easy object to image, and it's not getting too low down in the evening sky. Even by March the 2nd, it'll be 45 degrees high before evening, at the time the evening twilight has disappeared. That's an image taken by Dan Bartlett in California on New Year's Day. The comet takes just under 7 years to orbit the Sun. And after Comet Leonard, it's the brightest comet predicted in the British Astronomical Association handbook until the end of December this year. So it's predicted to be reasonably bright. And that's all I've got for you this month. So thanks, and let's keep our fingers crossed for the rest of the JWST deployment. Thanks.
Thank you, Alan. Can we thank Alan for that? So if you think you can, sorry, Alan?
Thanks very much.
Okay. If you think you can't do astronomy from the city, well, those pictures say otherwise. A lot of those images were taken from the centre or around about Edinburgh. So with modern techniques and filters and cameras, you can certainly do that. I also say that it's the responsibility of every president of the society to come up with a nice bright comet. Andrew came up with Comet Neowise during his tenure. I came up with Leonard, but unfortunately it was only nice once it was in the southern hemisphere. So I'll definitely have to work harder.
I think so.
Keep trying.
Okay, we have two things to do, which before we finish, which is we'll go through quite quickly. Will, do you want to get ready for this? Will, when he gave his talk about meteorites in December, set a meteorite or meteorong identification quiz, and there's no prize, I believe, Will. So I can put the slideshow up for you if you want to.
Absolutely, yeah. Go ahead.
See that?
Marvelous. Thanks very much. Well, first of all, thank you all for entering this competition. And these are the meteorites and meteorongs. So from the top right is number 1, and the bottom, top left is number 1, and the bottom right is number 10. So very quickly, I'll just go through. And tell you which they are. So going from number 10. That is a piece of rock which I found near Dunkeld on the A9 driving up to the Highlands, stopped my car, raced back, picked it up, and it's a meteorong, piece of igneous rock. Number 9 is a piece of rock I stared at for 2 days. It was on a low roof outside my kitchen window, and I couldn't believe it. Eventually, I put my white gloves on, climbed out, photographed it, picked it up, and it was as light as a feather. A seagull must have dropped it. So it's a piece of plastic or a piece of jet. Number 8 is a piece of basically fossilized coral found in the Arabian Peninsula, but it's got nice markings on it. It's meteorong. Number 7 is a piece of glassy slag, very light, which I found on the water of Leith. Number 5 is a piece of gravelly material, which is actually from a gravel bearing bed which contains diamonds and gold in Uchunga goldfield from Adelaide. So it's a meteorong. No gold or diamonds, unfortunately. Then we go to number 4 is number 5 is a piece of this is actually a piece of shale found near Bamborough Castle, a beach-worn shale. It's got little bits of iron in it, so it's a meteorong. Then we go to number 4, and this is a meteorite. And this was found in the Arabian Peninsula. And if you look closely, you can actually see a little bit of secondary fusion crust on that. Number 3, which a number of you mentioned, is, I believe, a piece of slag. I found this in Fife on an excursion near Glenducky. And so that's a meteorong, but I'm looking at it, and I need to do a nickel test because something is dragging me back to that, even though I strongly believe it's a piece of slag. Number 2 is a rock which I found on Leaf Walk, and it's a piece of road rock which has been cut. And number 1 is a second meteorite which is found again in the Arabian Peninsula. So answers 1 and 4. Now, no one got them right. So what I've done is I've split it up. There's going to be 2 prizes for the people who got number 4. I've got them all in here. Shake them. Names are in here, and I should draw it out. So just shake it out. Just randomly drawn one out, so we see who that is. And if I can open it. And it's Randall Stevenson. So well done, Randall. You've got 1 for getting number 4. And then secondly, for the people who got number 1 right, well, there was actually only 1. So it's here. And this person goes to, who it is, it's actually Karen Christie from Comanche in Oklahoma. So I shall make sure that these meteorites get sent away. Thank you.
Thank you, Will. Congratulations to your winners. So the last thing we have to do is, as you know, we've been running an image of the quarter competition for our imaging and observing group. And this is the first time we've run it. The prize, I think, Neil, is a gift voucher. I don't think we've decided where it's from, but maybe the winner can choose which we can offer a few options and see which one they would like best, whoever the winner is. There were 14 entries. I know there are an awful lot more excellent pictures in the Flickr group for the society, but that's all there were emptied for it. So there were loads of criteria I could have used for judging this, and it was incredibly difficult to do. I wish I hadn't taken it on now, to be honest. So I just went with gut reaction in the end, to be honest. So it's just the one that stood out and I really just liked, the one that jumped out at me. So I'll briefly go through each one. Each one of these has a little narrative with it that the person provided. I'm not going to read them out now. I'll put this on the report for this meeting on the website, and you can read them yourself. But this is the Horsehead Nebula and Flame Nebula from David Harvey. I should say all of these images could have won for various reasons. This is a very beautiful classic view, nicely colored, nicely processed, nicely composed as well. This is the Hidden Galaxy from Nigel Goodman. This is actually, I've tried to image this a number of times. It's a really tricky one. This is hidden behind a lot of dust and gas in our Milky Way. And if it wasn't so badly hidden, it would actually be a really bright galaxy in our sky. So I know it's really difficult to capture, and Nigel's done a great job with that one. This is the Cygnus Wall, part of the North America Nebula in Cygnus that Ian Smith's done, and that's beautifully processed. It's in the Hubble palette, lots of subtle shading and coloring, and good contrast in the darker areas as well. This is a really tricky one, quite a deep one from Mike McGovern. These are the ARP 273 galaxies. There's been quite a bit of discussion on the group about that. Very, very tricky to do, but he's processed that well, and it's a nice, colourful jewel box, really, that one. Pat Devine's done the Jellyfish Nebula. I've focused on a little bit closer. Amazing amount of detail and a huge amount of capture and processing done there as well. A lot of skill. Again, taken from the centre of Edinburgh. This one is the Iris Nebula by Ron Morley. A very tricky one to do. There's a lot of faint gas and dust around about that, and perhaps Ron's done really well to capture that one. Again, I find that quite a tricky one to image. Another one from Ian Smith. These are the ghosts of Cassiopeia. That's a sort of a Scooby-Doo ghost in a white sheet, really, that one. Again, quite a tricky one to capture as well, but Ian's processed that really well and captured that. Ian has the advantage of being an East Lothian, so he doesn't have to fight the Edinburgh skies. This one's really interesting from Hugh Somerville. Hugh said something. It was just a sort of a quick shot with his phone through his telescope, and he quite liked the result. When I saw that, I thought it's a bit like that old movie, or a Flash Gordon movie or something like that. But it's really quite entertaining, quite a good shot actually. This one from Fran Goodman, again in East Lothian, so she hasn't had to fight the Edinburgh skies, but that's a really nice composition of Orion rising with the lovely contrast of the trees in front of that as well. So that's the sort of the notification that winter's on its way when you see Orion rising. This one from Bill Bonner. Bill has gone through various telescopes, he says, but he just recently got this, and within a few days he was producing images like this with his new telescope, and that's actually a mosaic, I believe. So putting that together from a brand new telescope, that's pretty impressive. Lots of subtle shading and detail in there. Another one of the Horsehead Nebula, quite a different method of processing from the previous one. This is done more as a sort of false color imaging, and that's from Pat Devine. Again, very striking, lots of detail in there, right from the center of Edinburgh again. the Lobster Claw Nebula. That one from Ian Smith, again done in false color narrowband imaging, and that there's a huge amount of detail on that. Bit of a tribble in there, that we call it a tribble, and a nice star cluster down here as well, and the claws of the lobster. And another one from Bill Bonner, the moon taken with his new telescope as well. Lots of contrast and detail, sharpness on that one as well. This is a very complex one. This is Pat Devine has done this at the Vale region. This is actually a mosaic of 6 panes. So there's a huge amount of work in that, 6 individual panes, but 4.5 hours split over 2 nights. So capturing that, processing it, and stitching it all together is quite a huge job, actually. So a lot of skill in that. And no, it's not Emma Raducanu, who seems to win everything at the moment. So the winner of the first image of the quarter competition is Fran Goodman. And the reason being, I just liked it. I saw that and it was so evocative. It's, you see Orion rising. The composition is lovely. The contrast with the trees, the wispy clouds. And it was a sort of a surprise capture for yourself. I believe you're actually looking the other way for an aurora and you just turned around and saw that. So take your bow, Fran. So I'm sure Neil will be in contact with you, and you can decide where you would like your gift voucher from to spend on whatever camera equipment or astronomy equipment you like.
Thank you very much. I don't really feel I deserve it, but thank you very much.
So we will have another image of the quarter competition. Entries are open now. Send them to me. It's for ASC members only, and we'll announce the other one in 3 months' time. Don't think you're not good enough. You definitely are good enough. I want to see everything. If you observe and draw, if you're an artist, then I'd like to see those as well. You know, anything can win. So keep going. So that's it for tonight. I'll stop the sharing. Unless there's anything else. Thank you very much, Rebecca. Thank you, Alan. Thank you, Will. And we'll see you at the next meeting later on in January. Good night.